Okay, guys, I think we're good to go. Welcome back. Hope you had a good break. Let's get started. As I said on Piazza, for those of you that didn't notice, I've started for this lecture. I'm running a quick trial of using Zoom as well as the streaming. So if you're using the streaming, it's all good. But if you want to use Zoom, there's instructions on Piazza about how to do that. The advantage of Zoom is only one thing, and that is that if you want to ask me a question, you can just interrupt me and speak out loud, okay? That's really the only reason why I've got it there, is so when we do the live coding, you can just interrupt and say, hey, why don't we do this? Or, hey, what does that mean? And it may just be a bit more dynamic than me relying entirely on watching the chat. So that's the hope. That's the hope. We'll see how it goes. Now, with that, let's move on with our slides here. What have we got? Just got a keyboard issue already. What's going on here? Hang on a sec. Yeah. There we go. All right. Good. Now, the first thing to mention was some of you wouldn't have noticed because you were pretty, like me, keen for the start of the break. You may not have noticed I gave an extra 1 hour lecture on Friday, Friday of week 6, where I went through the whole of the mid-semester exam, just taking one question, one example of each question, and working through it, trying as far as I could to get your engagement with it and work through it the way that made sense. So I try to talk through it carefully and as reasonably and slowly as I could. I've got feedback that suggests that was popular, that you like that. If you didn't see it, I highly recommend you take a look, particularly if you were not, if you're a bit disappointed in your result, you might find it very useful to see how I step through things. Please, as I've said many times before, I have a strong view that there's no sort of right answer. The way I did it in that lecture is only one way to do it. And as someone pointed out in Piazza, I made at least one mistake that wasn't picked up by the tests when I was going through that coding. So they're not gospel truth or anything. That's just one way you can work through those questions. The other thing to say about that is I put all of the questions, which is 20 questions, so that's on average 5 examples for each of the 4 questions. I put them all on GitLab. And so you can all go through them, and I really think they're probably a pretty good resource for revision, and it might be really worth your while just stepping through those. Particularly if you were a bit disappointed in how you went, what I would highly recommend is you go through the questions that you had in your exam, go through them in your own time as slowly and calmly as you want. And then once you feel like you're on top of that, go and do some of the other example questions. Go and do some of the other example questions because they're similar, but they're different. So that will give you another chance to test yourself on those. And then if you wanted to, you could do them under time pressure if you wanted to get a sense of how fluent you were with these things. The first... Katrina asked if the guest lectures are accessible. Yeah, they are, but they're not worth very much, okay? So you're expected to have watched them. I'm not going to ask you questions like when the speaker's birth date was, but nor am I going to ask you questions about some finicky part of their technical stuff. I'm only going to ever ask you big picture questions, okay? Really big picture ones, like what were the key things you learned or whatever. So don't stress. I know that Amanda's lecture was really pretty full on technical. She hasn't given a lecture to undergrad computer scientists before, I don't think. So I didn't quite realize that, but so it may have been a little full on with the machine learning and so forth. Don't stress about that. I'm not going to ask you anything crazy. You don't need to go there and memorize that whole lecture, and it's only worth a very small amount. The guest lectures are really there for you to broaden your experience of computer science. If you just got blown away by the whole thing and thought that it was just too much, prioritize on other things. Don't worry about it, okay? Move on to other things, because if they are assessed, it'll only be a small assessment. And when I say if they are assessed, they're nominally assessed, but normally I have multiple choice questions in the final exam. Because we've got an open exam, because you guys are doing it remotely this semester, I'm not sure I'm going to have multiple choice questions or not. I haven't finalized my decision on that. And if I don't, I'm certainly not going to have coding questions on the guest lectures. So at this stage, I'm not 100% sure whether or not there will be questions on the guest lectures, but nominally they're accessible, okay? and that's why it's on the slide. Yep. All right. And 3% per lecture. That's 3% not of your marks. That's 3% of the entire body of work of the course, right? And what that means is that you should very roughly expect about 3% of the exam to be on this stuff. But I don't think even that's. I think that's an overstatement. I think it's going to be even less, and it may be 0 because of the fact that you're doing it remotely. Okay. Hopefully, I answered that question for you, Katrina. Hopefully, you've all figured out assignment 2, the deliverable, how to do your contribution statements. I know there are a few groups who are having significant stresses about group dynamics and who's doing what work. Look, I know it sucks. I know it's hard. There are 2 members of my family right now who are doing group assignments. One at a graduate level and one at a high school level, and they both have rough experiences. Okay, so I'm totally on board with you on that. Unfortunately, in this class and in other disciplines like engineering and software engineering, working out how to work as a group is actually part of the course. So we are actually assessing you on your ability to work as a group. So it can be very rough, and if you need help, like you reach out to your tutor or reach out to me. But part of what you're supposed to be doing is dealing with these difficulties as gracefully as you can, and doing things like dividing the marks up in a way that actually reflects what work was done. So if there are people who are just not doing anything, that should be reflected in the division of marks. Okay, that's there to protect you. Any other admin questions before I launch into the body of the course? And remember, if you're on Zoom, you can just feel free to unmute and yell a question. All right, if there's nothing else, I'll move on. The good news is, folks, we're basically done with Java. We've only got 2 modules of Java left. One, hopefully, we'll do today. At least we'll start today. That's J14. And the last one is J15, which we'll do right at the end, which is really about threading and concurrency, which we're not going to do until right at the end of semester. So essentially, the body of Java is all done. We did that before the semester break. So now we move on to a whole new level of stuff. Are you going to be assessed on D2D in the lab? Yeah, I think that's right. I think, sorry, this is just going back to an admin question here on the chat. Did you start every lab with 30 minutes with your tutor? Your tutor has 30 minutes with you, and that will, I expect your tutor will talk to you individually about whatever you did for D2D, okay? So that should happen in your lab. And certainly your tutor's looking at it since you submitted it, and they should be able to talk to you about it during your lab. That's the big idea. You should be getting feedback on that. As you noticed, D2D is not worth very many marks, but it is individual. It's really just a checkpoint to try to gauge that everyone is doing something in the assignment, and that everyone and that there's no one in the group who's completely lost. That's really what it's about. One more. For one guest lecture, it said, yeah, sorry, that was a really good question. Someone asked a question. Oh, by the way, I'm not reading the chat in Zoom, folks. So if you're on Zoom, please don't put questions in the chat there, just because I can't manage that as well as looking at Teams. So if you have questions and you're on Zoom, can you just put the questions in the Teams chat, please? I just can't do 2 chat channels at once and do the lecture and watch the Zoom. Sorry, one more admin question here. And that was whether or not the 1140 lecture was examinable for everyone. That's the one about games, right? And they looked at the game for 1140, and the answer is no, it isn't. That's only accessible for the 1140 students. Okay, so good question, but the answer is that the 1140 guest lecture, which was the first one, is only accessible for 1140 students. So if you're not in 1140, you do not need to see that lecture. You do not need to revise it or anything. So the only one you need to do a revise is the Amanda one. And when I say revise, it's sufficient just to watch the lecture once, take some notes. That's enough, right? You don't need anything more than that, okay? You certainly don't need to go look stuff up and do background reading or anything like that, okay? This is not supposed to be a big deal. Okay, all right. Let's get on to this. This is what I really want to talk about. I actually enjoy the second part of this semester a lot because we're done with all the nitty-gritty about what a for loop looks like, what an if statement looks like, and we start moving on to things that are a little bit more substantive, okay? And now what we're doing is we're moving on to talk about abstract data types. Okay, and so this is kind of fun, and it's a key part of this course. We introduced some of these ideas in the first part of the semester when we talked about things like lists, sets, and maps. Okay, and we talked about them in terms of what Java offers in its standard libraries. Now we're going to another whole level and trying to understand these data structures a lot more deeply, and we're going to implement them ourselves. And I've said it to you a few times, I'll say it one more time. We're implementing them ourselves for one reason only, and that's so that you can understand them, right? Okay, it does not make sense. If you go out, finish your degree, and go out and start programming, do not go and implement a hash map yourself unless you have an extremely good reason. Use the standard library. Why is that? Can anyone want to answer that? And if you're on Zoom, feel free to just unmute and shout your answer. Why would you not go and implement a hash map yourself? Why would you use the standard library? Anyone?
The standard library is tested.
Yeah, that's exactly right. Standard library is tested, and it's tested at least two ways, right? It's tested for correctness and it's tested for performance. Okay, it's tested for correctness and it's tested for performance, right? So which means that it's going to be about as fast as you can possibly imagine, and it's going to be really, really sound. And how tested is it? Well, you know, I've told you before how I worked in the summer at Google on the Chrome, on V8, which is the engine that drives Chrome. And one of the things that I found coolest is that when we put code in the code base, it got tested enormously. It got tested by thousands and thousands and thousands of tests. You know, you guys get 5 tests for each of these things. Whenever I submitted a tiny bit of code, when I just did like my CI, the CI that I did, in fact, before the CI, before I even uploaded for the CI, it would go through about 5,000 tests. And when I got ready for the CI, it was 15,000 tests. That's how many tests it would do. When it did that, it would go into another level of testing, which would be even more. And then finally, it would get tested by the users. And you know how many users it had? It had 1 billion with a B, 1 billion users. So that means that this code is really, really, really sound. Okay, it's been extremely well tested, both for performance and for correctness. Okay, Twitch and YouTube are having problems. Sorry, I'm not sure what that's about. Actually, I can see on my streaming thing, I can see it changing color and showing some issues there. Now, what I might do, I'm going to do an experiment, folks. What I might do is kill the video on Zoom. Okay, sorry, folks on Zoom. I'm going to get you to jump onto the streaming service. I'm going to kill the video on Zoom so you can't see me. That's because I'm concerned that that Zoom is hogging the bandwidth and killing the streaming for everyone. Okay, so I've just gone and killed it, and you'll just need to look on something else. If that solves the problems, then we'll continue. Otherwise, we can try something else. I can see now the window, the monitor I have on the streaming thing is now looking good. It was much worse a moment ago. Yeah. Okay. The problem there is Zoom. Zoom is hogging the bandwidth. So I'll explore if I can improve this later, so you can watch the video on Zoom. But for now, I don't think I have much choice. I don't want to kill the video for everyone on the streaming service just to get the Zoom working. All right. So at the moment, there's no picture on Zoom. So apologies for that. All right. Back to this. So hopefully everyone has a clue about what the ADTs are about, and why you use the standard library rather than building everything yourself. And hopefully you also understand why we're implementing them ourselves in this class. All right, what is an abstract data type? Now I want you to concentrate on this because this is important. Abstract data types describe the behavior of a data type without specifying its implementation. Read that line carefully, okay? So what it's doing is it's saying, here is the thing which has the following behaviors, but I'm not going to tell you how it's implemented. Okay, so if you think about, so then I'll ask the question, is a hash map an abstract data type according to this definition? Anyone want to venture an answer to that? Is a hash map an abstract data type in terms of this definition? Anyone want to venture an answer to that? Nope. The answer is no. Why not? Because a hash map actually, yeah, someone's already answered, good. The reason why it's not is because a hash map actually does describe the implementation. When we say hash map, we're not just talking about any old map, we're talking about one that's implemented in a particular way using a hash map, okay? Which we're going to using a hash table, which we're going to go and work with later in the next few weeks, okay? So when we say hash map as opposed to map, we're talking about a specific concrete version of a map. Okay, so the map, according to this definition, is the abstract idea of a map. It's an ADT, right? Abstract data type is the map. The hash map is a concrete example of one of those, okay? So I just want you to be really clear about that. Yep, so someone said in the chat, map is the ADT, and according to this definition of an ADT, we would describe the hash map as not being an ADT, but an instance, an implementation of a map ADT. A container is is a very general ADT, just using the word container, and it serves as a holder of objects. You can think of it like that, okay? And you can think of a list as an example of a specific container ADT, okay? So a list is a kind of container ADT, and a set is another kind of container ADT, and a map is another kind of container ADT, okay? And then an ADT is described in terms of the semantics of the properties that may be performed on it, okay? So semantics is the computer sciencey word for behavior, right? It's like the formal way of describing the behavior of this thing. So let's first look at the list ADT. A list ADT is a container known mathematically as a finite sequence of elements, okay? It's got the following properties. You can have duplicates. So I can have a list that can have apple, banana, apple. That's a list, and it's got 3 things in it. 2 apples and a banana in the sequence, apple, banana, apple. A list maintains order, okay? So there's a defined order to a list. If I add something to a list and add an apple to a list, add a banana to a list, add an apple, then what the list will show is in exactly that order, apple, banana, apple, okay? A list may support operations such as create to make an empty one, add to add something to the list, and a test to see whether it's empty. There could be other operations as well. So there we go. And what we're going to do in this class is we're going to use this interface here, this interface for lists, okay? There's one thing missing from here. No, it's good. I was going to say it's missing remove. Oh, one thing, no, it's all good. It's all good. So we're going to use this interface here. There's one other thing that is here that's not explicit. What's the thing? Can anyone know what other function we're going to have on our list, which is not actually on the slide, but it's actually there implicitly? It's a toString. Okay, we're going to have toString as well as those ones there. And so in a short while, we're going to start coding, and we're going to use this interface. This is different and simpler than the standard one that Java provides. Notice 2 things here. Okay, first of all, notice that this is generic. See that T there? The T says it's not being specific about which type. Remember the discussion about generics? Remember the pickle truck? And the idea that we don't want to build everything that's nailed down to be for a specific type, but rather we want to use generics, okay? We want to use generics, which gives us the ability to make a single list that can be used for integers, for characters, for strings, for COMP1110 students, or whatever it might be, okay? And that's what this is, okay? That's what the T is, all right? And then we've got these functions here, add something to the list, get something at a specified index out of the list, size tells us how big the list is, remove takes something at a given index out of the list, and reverse flips the order of the list. Remember, lists have an order, okay? And we're going to use that interface. I'm going to code that up, and we're going to implement this 2 different ways. Now, can anyone think of 2 different ways of implementing a list? I've already given you lots of clues about this, and I think you've even seen it somewhere. What are 2 different standard ways of implementing a list? Can anyone think of 2 different? Anyone make a suggestion? Anyone want to shout on the on Zoom? For those of you who are watching on Zoom, listening on Zoom, you should be able to use the audio on Zoom and the video on the stream. Yeah, a linked list is a great example. Okay, so you can use a linked list. And what does a linked list do? Hopefully everyone has an idea of a linked list. I'm going to show you. Actually, I think I have. I'm just going to quickly visualize one here for you. Have it here. Yeah. Okay, so here, the visualizer doesn't do this very well, unfortunately, but you can see here, we've got ourselves a linked list. It's got the first element of the list here, which refers to this guy, which is a list node. Then you've got another element of the list here, and another element of the list here, and another element of the list here. Notice that each node in this list has a value. In this case, it's A, B, C, and D. They're the values. And then we've got a next pointer. Okay? So, yeah. You don't see the visualizer. Maybe it's just lagging. Okay, so you should be able to see the Java visualizer. It's probably just lagging. You should have seen the Java visualizer. I can see it going out on the stream. All right, so that's yeah. And someone says recursive data type. Well, a linked list is a recursive data type. Why? Well, let's have a quick look. Let's go back to that example. What you see is that one of the elements of you've got a linked list instance here. What type is that there? That next guy is of type linked list. So it's a type that refers to itself. Okay. All right, so let's move on. Now, let's go and look at visualize the behavior, the semantics of each of the of each of these things. So I'm just looking at the chat here, and everyone's having issues with streaming. What I see now, since I stopped Zoom, it looks like the streaming is very happy. Okay. So what we have here is we want to add a value. We're going to add D, right? So hopefully you can see this visualization. And what I'm visualizing is a list there. It's got 3 elements in it. It's got an A, a B, a C. Okay, and then we're going to add a D. And then that's what it looks like after we've added the D, like that. And now we're going to do a get operation. What's a get going to do? It's going to take an index. In this case, it's 2. So we're going to go to the element that's at index 2, which is, in this case, C. Okay? So it returns the letter C. Notice I've got the little red highlight there on C. And size, what's size going to do here? It's going to tell us the size of this list, which in this case is going to be 4. Okay? Remove, it's going to take an index for a particular element that we're going to remove. In this case, we're going to remove element number 2, which would be C. So we're going to take C out, and we end up with that. Yeah, I don't know why YouTube's latency is so bad, folks. I'm afraid there's not too much I can do about it. What's a reverse operation going to do? It's going to take a list like that, which is A, B, and D, and it's going to flip it around like that, D, B, A. All right, and then we've got a toString operation, which will take D, B, A, and it will produce that. Okay, D, B, A. So that's the behavior we're going to see for our list. Now, how are we going to implement this? I asked you a moment ago about the array list, about how you could implement it, and people correctly said there are 2 standard ways to implement a list. One is an array list, and one is a linked list. Okay, so does anyone want to venture something about what is good about an array list? So an array, let's just recap what they are first, okay? So we looked at a linked list a second ago. I showed it to you in the Java Visualizer. A linked list is a whole series of nodes like this, okay? So what's the advantage of a linked list? Anyone can say, in terms of these operations, what's kind of nice about a linked list? Yeah, a linked list is fast with respect to what? Anyone? Don't forget to speak up on Zoom if you want. That was the intention of Zoom. You could just jump in with an answer. Nope. Okay, so when I give this lecture and a lecture there, I really expect you got, yeah, good. Go ahead, say it again.
Insertion and deletion of elements.
Yeah, perfect. Exactly. That's exactly where it's good, right? Adding or removing elements, insertion and deletion. That's exactly where it's good, right? It's really great for that. What about if I want to get the 4th element of the list? If I want to get the 4th element of the list, how many operations is that going to take for a linked list? How do I do that?
4.
It's going to take, it's going to take 4, right? You walk down that list 4 times, right? And you're going to get it. Going to get it after 4 steps. On the other hand, if I want to get something out of an array list, how many operations is it?
1.
Yeah. Okay. Now, what's the difference between 4 and 1? No big deal in the context of 4 and 1. Okay. So yeah. So someone's written there that it's order n. We're going to do complexity later in this semester, but that's exactly right. If I've got a list of size n, then the time it takes to find a single element in that list to get element number k in that list is order n, which means that on average it's going to be half the length of the list. Okay, if I take a random element in the list, I've got a list of length n, okay, and I look for element k, and I take a random k that's somewhere in there, on average it's going to be halfway, right? Which means that it's on average n divided by 2, which means it's order n. Okay, so this is a very, very slow. Okay, it's perfectly fine when you've just got the apple, banana, and apple, right? But think about the case where you've got a lot more elements in your list. Now, think back to the example we did at the end of last semester with Boggle. Okay, if you remember there, we had a list of words, or was it a set of words? I can't remember, but it had, I think it was like 15,000 words in it, right? Now, 15,000 is a very different story to 4, okay? So if I've got to go and look up the 14,000th word, and I've got to walk down 14,000 letters before I get to it, that's going to really suck. That's going to be terrible, right? So I don't want to use a linked list if I've got 14,000 elements in my list and I want to find the one right near the end. Someone asked, why will remove 2 give B? That looks like a typo. Thank you for calling that out. That someone's pointing to this B here. I don't know why the B is there. I'd need to check. I don't have a good answer. I don't know if there should be any answer to that. Yeah, so I don't know. I think it should return C. I think it should return the thing that got removed, right? So when you say yes, it should have returned a C. That there should be a C. Okay, so I can't fix it right now, but that should be a C right here. Okay. Well spotted. All right, so that's a linked list. Now the array list, on the other hand, is going to use an array. Okay, which means that when I want to find the 14,000 element, I can get it in one step. Okay, I don't need to take 14,000 steps down this list to get to that array element, right? Huge advantage, massively better. On the other hand, what's the disadvantage? Someone already said there was some of you already mentioned the advantages of linked lists. There's a corresponding disadvantage to an array list. What's the disadvantage to an array list? Anyone? There's a clear disadvantage to array lists compared to linked lists.
Add
Yeah.
in the middle of a list.
Yeah. If you want to add something, somehow either you've got to grow the array, or you make the array bigger than you need it, or what? It's complicated, right? It's not simply a matter of adding something on the end of the list. It's not dynamic, as someone just put on the thing. Okay, it's not dynamic. You've got to have this array, and then if someone wants to grow it, you've got a sort of interesting or tricky question about what you do when someone goes beyond the end of it. Okay, so one possibility is you make a whole new array, copy all those things over into the new array, and make this new array a bit bigger. How big? Well, I don't know. You have to make a call about how big. It's a tricky question. Okay, so can you make a linked list of array lists? That's a good question, maybe, but we don't normally. Okay, but that's a problem. Yeah, someone said it very. Harriet said it very clearly. It's harder to increase the size. Not only that, but it's also harder to reduce the size. Okay, if I remove an element and I want to make everything go back, I've got to slide everything over the top. Whereas with a linked list, I can just pluck one of the elements of the linked list out. Okay, so hopefully you've now got a sense of what the pros and cons are of these two completely different approaches to implementing the abstract data type of list. So the abstract data type in this case is a list. We've got two concrete examples, a linked list and an array list. They both have advantages. Most commonly, we use the array list because the advantages in the array list are typically the ones we care about most. Sometimes, though, a linked list might be a better choice. And if you understand that, then when you go out and start programming for real, you can choose in the Java Standard Library between an array list and a linked list and know exactly what's going to happen and exactly when one's going to perform well and the other one isn't. Okay? So here they are. Arrays are fast to look up any element. You get it in one step. They're messy to grow and contract. A linked list is a logical fit to a list because it's easy to grow, easy to contract, but you need to traverse the entire list, or you need to traverse the list up to that point to find any given element. Okay, so that summarizes all the pros and cons we just discussed. So here's the mini quiz. Let me publish this. Mini quiz. There it is. Okay, the mini quiz, you should be able to see that on Piazza right now. And with that, we can move on and get on to coding. And we're going to start a whole new unit here. We're starting the A series. A stands for abstract data types. Package A01. There we are. Now the first thing we're going to do is we're going to create an interface type. Okay, an interface type. So new Java class, and we're going to call it list. Okay. Now, at this point, the whole thing about namespaces, which I think I mentioned in the very, very first lecture when I talked about Mary, Queen of Scots, and the idea of identifying things by name, this thing up the top here that says package, it becomes incredibly important now because you've got multiple versions of list. You've got Java's own notion of a list, and we've got our notion of a list. Our notion of a list has this stuff in front of it, okay? It says COMP1110 lectures A01 list, okay? That's a different list to Java util list or whatever it is, okay? So I just made a mistake there. This is not supposed to be a class, okay? First, I was distracted as I typed that. This should be an interface, right? And the other thing I'm going to do is what other thing have I got wrong here? There's something else we want to do if we're going to do it the way we talked about before. There's a key idea that I've missed. Can anyone see in what I've written already? There's something missing. We want to make this generic, okay? We want to make a list that works for multiple different types. And if we do that, we want to declare it as a generic list, okay? So it means we do this, okay? That's the way we declare something as being generic, okay? Yeah, someone's already written that in the chat. Oh, there's another question here. Is it better to stick to just an array or to a list? Oh, you mean, is it better to just use a Java array? Well, the thing about a list is it gives you lots of other functions, okay? It's an interesting question. Well, if you use an array, it's simple and fast, and you know exactly what it's going to do, but you miss a whole lot of features. So if you're doing something simple, it may be best to use, if you know exactly what you're doing and you only need the features of an array, might as well use that if you're worried about performance and all the rest of it. But more generally, it's often a good idea you use lists, okay? So, good question. Good question. But the general answer is prefer to use lists. Okay. So let's write our function here. It's very simple. Public void add, and it takes t and the value. Okay. Then we've got what's the next thing we're going to have? We're going to have remove. So it's going to be public like void. Actually, no. We said void here. Maybe. In the example where the person asked the question about the slide, we actually returned a type. So I'm confused here. Yeah. Well, at the moment we'll just return void because that's what I've got in my notes. But we could return the thing that we removed. That's another possibility. But in this example, we're just going to say remove, and return nothing. Okay. So we're going to index int index like that, and then public size. Okay, that's the size of the list, and then we're going to do a get, which is going to pull that thing out. So public. If it's supposed to be a void, then that answers the question the person asked about removing. Yuhao asked a question about why removing 2 would give a b. It should just be void, I think, if what Linda wrote is correct. Okay, so we're going to do size. Then after that, we're going to do type t get. So it's going to return a thing of type t. It's a get, and you're going to give the index of the thing you want to get out of here, like that. And then we're going to do a reverse public void reverse. And a reverse is going to flip the order of the list. And public string to string. Now what we're going to do in this lecture is, for the coding for this module, is we're going to do an array list. Okay, in the next module, A02, we're going to do a linked list. Okay, now, but what did I just teach you? I taught you something right, I think in week 5 about test-driven development. What should we be doing in test-driven development? Anyone? What's the deal with test-driven development? You always build the test before you build the implementation, okay? And that's something I want to really encourage you to think about and encourage you to actually do in practice. Yeah, write tests before you start coding. So we're actually going to do that now. But the first thing we'll do is make the 2 empty classes. So that's array list. Implements list. And now notice I've got to choose the right one, not Java util list, but COMP1110 A1. Okay, like that, and then it invites us to implement the methods. Okay, there it is. Okay, so that's all the methods implemented. So now we have an empty implementation which does nothing, and then we're going to write also. We're going to implement an empty linked list. Like that, and we'll add it to Git, and we'll also extend implements the interface list. Okay, it's our interface there. And I should have said these things are generic too. Like that. Like that, and then implement the missing methods. Like that. Okay. Now let's make sure I did it the right way with the array list. Oops, I just typed the wrong key. Still haven't got a decent keyboard here. No, I forgot to do this. So I need to change this. Let's just get rid of all these here. So we'll do this all over again. We'll make sure it's generic. It's going to be generic in T, and that's going to be T like that. And then what we'll do is we'll say implement the methods, and this time it will do it with the generics. There you go. Okay, so we have that. So now we have two stub implementations. Does toString need to be defined in interface? No, it doesn't. I noticed that I did do that. We can just leave that out. In fact, you'll notice also that IntelliJ just completely ignored it. Okay. I don't think it did. Yes, it didn't. So IntelliJ, when it filled it out, it didn't even put in the toString. Okay, because there's a toString in object, so it doesn't need to put one in there to fulfill the interface. So putting it in interface is actually completely meaningless. So I've just removed it from the interface because it's completely meaningless to put it in there because it's actually already provided by Java Lang object. I'm just responding to Adam's question about whether or not we needed toString, and I've just gone and deleted it because it's actually quite unnecessary. And I was just thinking that as I looked at IntelliJ filling these out, notice it didn't put toString in there. All right. Okay, hopefully everyone's up with where we are now. We've gone and defined ourselves an abstract data type, which is the list thing. We've gone and made two concrete ones here, which have nothing in them yet. They're empty. And now we're going to write a class, which is going to be our test class. Okay, so we're going to write a class here, new Java class. And we'll call it list test. Okay. And we'll add it to Git. There it is. And then what we're going to have at the top here is we're going to have a boolean which allows us to test either the array list or the linked list. Okay, so we say private boolean. Actually, why don't we make that static? And if it's not the array list, then it will be the linked list. Okay, so all that is going to do is going to be a flag that will change to test either the array list or the linked list. Okay, it's just a flag. That's all it is. Okay, so now let's write ourselves some tests. What we want to do is we want to write a test for each of the things in the interface. So let's just start off by writing test. There it is. Test public void test add. So we'll write a test here for add. We won't write it yet. We'll just do it in a second. We'll write another test for public void. So while I'm typing this in, I want you to think about and be prepared to yell out on Zoom what you think we should be writing here in terms of the test, how we should be testing it. Okay, test remove like this. Test get. Okay, we're going to write all these tests out here. And what else have we got here? We've got test get, remove, and reverse. They're the key ones. Okay, so now we have the empty methods there. And oh, okay, so that was the question I asked before, whether or not it was going to return that. That's why the slide. So Brendan's written here on the message that it does return the remove does return the instance that got removed. We can change that, you know. So why not do that? Okay, that was the question I asked earlier. So let's just do that. Let's do that, and then get these ones to be fixed here. Where's remove? Okay. Let's implement it the way we'll just return a null here. Okay, so Brendan just pointed out that the Java 1 returns the element that got removed, which makes sense to me. And that's what I was a little bit confused about because my notes didn't have that, but the PowerPoint slide did have it returning something. However, the PowerPoint slide seemed to be wrong because it seemed to be returning B. It should have returned C. So like that. Okay. What did changing void to T do again? Which void? So, oh, here. Okay, so someone's asking about this here. So what we're doing now, following on from what Brendan said, we had a little discussion, a little digression earlier. If you look back here, I'm going to fix this slide right now because this is irritating me and you guys are asking about it. So let's just dive in here and fix the slide right now. That should be a C. Someone pointed this out right when I was showing that slide. Let's get back and show the slide. Okay, there it is. Let's get step through here. Okay, so remove, right? Notice the way it's written in the slide here. It's got a T there, which means that when you remove something, it's expected to return something, okay? Or an element of type T, okay? And if you look here, what Brendan has pointed out is in the documentation, it says it will remove whatever element. It'll return whatever element got removed. And in this instance here, we're going to remove element 2, which is this 0, 1, 2. So it's C, okay? C should get taken out of this list and returned as a return value. So that we take it out and return C, right? And previously there was an error. It was returning B. Okay, so fix that error. Now it's returning C, okay? That's what that was all about. Now flip back to the code. I went and changed the code to reflect that. That had void before, so it wasn't returning anything. Now we've changed our this is the relevant one here. So what we've done is we've changed remove. We've changed the behavior of remove. Instead of doing nothing, it returns the element that was taken out. Now someone's saying test reversed empty list, single element list. What's that? Oh, that's an example of a list. Great. Yeah. Okay. Good. Someone's giving suggestions for lists. Great call. Okay. All right. Let's get on and write some stuff. So we already have one suggestion here. Empty list. I'll just write that as a comment because we'll do reverse later. Okay. But I'll write those comments in there. What is it? Empty list. Empty, comma, single element list. Okay. So what happens when you have those? Test remove should try to remove an element from, should try to remove as a failing test. Yeah. Now, one thing we're going to do, that's a good question, Adam. So one thing we're going to do, folks, later on, I can't spell element. Okay, we're going to remove, someone suggested we should remove a non-existent element. That's another good suggestion. Does anyone else have suggestions for what tests we do? If you do, just put them in the chat or speak out loud. I mean, if people don't want to use Zoom to speak out loud, that's cool. We'll just not use Zoom in the future because it's obviously hogging bandwidth anyway. But if you want it to speak out loud, it does make the lecture more dynamic, so I'm kind of keen on you doing that. But, all right, so test add... Okay, so let's start writing this, okay? Let's write some tests. Now, one of the really important points here is that we can't, in this class, in the time that we have available, write comprehensive tests. Okay, I just gave you an example a few minutes ago about how something like V8, when you run a very simple thing, you get 5,000 tests or 15,000 tests. We can't possibly do that right here, okay? So, so null list in all of the tests, that's a good suggestion. Okay. All right. Okay. Using Zoom without the video is hard because it's out of sync with the streams. Good. Yeah. Good point. I'm not sure we have a good answer for that. Maybe Zoom's just not going to work with the amount of bandwidth I've got from my house. Okay. All right. Anyway, it was worth the experiment. I'll see if I can throttle the video on Zoom somehow or other so it doesn't use as much bandwidth, and we can try that next lecture. All right, so now we're going to do some very simple examples. Get an element out of bounds. Yep. Get. Now, Linda suggested that. Now, it's an interesting point, Linda, because the very next unit we're going to do is J after, we're going to do A0, A1, A2, then we're going to do J15, okay? And J15 is... Well, let me not answer that. But what do you think should happen when we get an element that's out of bounds? Linda suggested that as a test, right? So what should happen then? Anyone want to say what we should do, what our program should do if that happens? Someone has asked to get an element out of bounds. What should our code do?
Throw an exception.
Perfect. It should throw an exception. Okay. It should throw an exception, right? So if we're going to throw an exception, right, so we should be throwing an exception. And what we're going to do in J15 is learn about exceptions, not only how they work, and how to generate them, how to handle them, but also how to write tests for them. We're not going to write tests for them in this lecture, in A01, but we're going to come back in J15 and add to these tests that actually check that our code throws exceptions in the cases where it should throw exceptions. Okay? So that's good. So what we're going to do as a result, Linda, we're not going to test out of bounds just yet. Okay? Because we're going to do that in J15. We're going to, I think, I might be wrong, but I think what we're going to do, what we're going to do is in J15 add tests that test the exception handling ability of our code. But we're not going to do them until we've learned how to do exceptions. That make sense? All right, so great suggestion. I will just add that note here. We'll do, oops, caps lock. We'll do in, okay? So we'll do that in J15. All right? And there are a number of other ones here that might throw exceptions, and all those ones we'll do in J15. All right, let's get on and write the test now. And actually, the null may come under that category here, J15 too. Okay, because that should just generate a null pointer exception, right? Sorry, null. Sorry, if it's the null list, you're just going to get a null pointer exception before it even gets this code, right? Someone suggested putting null in here. Okay, so think about it. If someone wants to call a, say, add on a null list, someone gives you a list and it's actually null, you'll get a null pointer exception before you get to test it, right? It won't even go to your code because there's no pointer there at all. Okay, so we can't actually test that here. Okay, we can't test for a null list when we're testing a list. All right, does that make sense? Hopefully that makes sense. If it doesn't, say something, and we'll come back to it later. All right, so let's write here. We're going to write in this class. We're just going to use strings, right? In our tests because they're simple and easy to see. You could use any type you want, but notice that we're testing generic lists, so we can do any type we want. So we're going to write a list here, and if it's an array, we're going to say new array list. Make sure it's the right one. Yep, that's the right one. Otherwise, we'll say new linked list. Okay, notice this line of code here. We've written it generically using an abstract data type, a list. We've said it's going to have strings in it. And then we've said, depending on whether this flag is true or false, depending on which one we want to test, we'll either create an array list or we'll create a linked list. Okay, and that's what that little, someone asked me earlier, what does this strange syntax mean? That question mark is a shorthand way of writing an if statement. It says, if that thing is true or false, if it's true, do this part, and then there's a colon, do that part if it's false. Okay, so that's what the syntax means. That's like an if statement. That's the true part. That's the false part. That's the condition. Okay, so if array is true, do this part. If it's false, do that part. So that allows us in our code to use the same code for testing both array lists and linked lists just by changing this flag up at the top here. Okay. Now, and in this class here, we're just going to test the array list because we're not going to work on the linked list yet. Okay, so let's keep moving. So what we're going to do first is, what do we know? What property can we test immediately? We've just made a new list. Okay, so we just made it on that line of code there. What can we say about that linked list right off the bat? What's the first thing we can test for straight away? It should have size 0, right? That's the very first thing we can say. So we can say assert true. If that's not true, we're in trouble, right? What's the formal name of the syntax? Can you just be a little bit clearer? I don't really understand your question, I'm afraid. Oops. There we go. Assert true. There it is. Okay. So we've asserted that the size of this new thing we just made is a size 0. Then we're going to add. Then let's add one string to it. So l.add, and we'll just add a simple string here like that. A. Okay. We're going to add a to the list. And then what we'll do is we'll say, what can we now assert? Now, there's a really interesting problem we've got here. And this is true whenever you do tests. When we're going to test, obviously we're writing tests here at the moment for add. Okay? But it's very hard to test add in isolation, right? Because to actually write the test, we might need to do things like check the size, right? So we're implicitly testing size. So I'll write a comment here. What else might we implicitly test here? Oh, I can't remember what the name of that syntax is. I think it's a shortcut conditional. I don't know. Someone else can tell you. Sorry, I can do a web search for it. What was it?
Ternary operator.
ternary operator? Well, it is a ternary operator, but that's a general form. Ternary operator means there's three things there. But that's true. That's absolutely true. It is a ternary operator, but I think there's a name for that it is a ternary operator, but I think there's a name for it, for that specific concrete ternary operator, but that's okay. If you do a web search for ternary operator and Java, you'll probably get it. All right, implicitly testing size. And what else are we going to test here? We're going to testing add explicitly. That's what the point of this test is. But we want to add something in, and we want to check if it's in there. How are we going to check that? Well, the minimal way we can do that. Okay. A get. Well, yeah, but that we've already got a thing down here for testing get. Is there a simple way to do it? Why don't we test toString? Okay, because toString is such a fundamental thing. So what we're going to do is we're going to test. We could use get, but then we've got a whole unit test down here for get. So let's implicitly test size and string. So these are the most basic things. If they don't work, we can't do any tests at all. So all these other tests will depend on these things here working. Okay, so we've already shown here that we're testing size, and we're going to add a, and then we're going to say. So what are we going to do now? We're going to say assert true size. L.size is what now? What should the size be? I've just added a. Size is going to be 1, right? I just added one element to the list, okay? And then what we can do is we can also do the toString method. Because the toString method is so fundamental, it's not unreasonable that we should assume that that's been implemented, okay? Obviously, if we implement it wrong, this whole thing's not going to work, so we will have to check it. But let's do that. So we're going to say assert true L.toString dot equals what? What should it be equal to? It should be equal to just this, a, just a string a. Okay? So that's what we should get. Of course, we can define, yeah, that's exactly right, Adam. Yep. So we've done that. Now let's add something else. What we're going to do now is we're going to cut and paste this code so we can speed ourselves up a bit here, because otherwise we're going to go too slow. Say BB, we're going to add another string which happens to have 2 letters in it. Now what should the size be? Okay. Yep. Yeah, I did explain the ternary operator when I went through the mid-semester exam, folks. So now what we're going to do is we're going to make our list just the toString operator. We've got to decide how we're going to do that. But the way we're going to do it in our class is we're just going to have a space between each of the elements in the list for the toString, just like that. Okay, it could be something else, but that's what we're going to do here. Okay, so it should be like that, and then we can do this. We can say add CCC, and then the size should be 3. And we should have CCC in there, okay? And that is a very, very basic test of add, okay? We haven't removed anything, because that would depend on remove being correct, which we haven't done yet. We haven't gotten anything, because that would depend on get, which we haven't done yet, and we haven't reversed anything, okay? So we're going to do those parts later. So this is a very, very simple test. You can see it's very minimal. Size equals 3. Size not equal to 3? Assert true, size equals 3. Is there a problem with that? What's up? That should be true, right? Someone's asking if that should not be equal to 3. I'm not quite sure why they're saying that. Maybe I've missed something. All right, now let's go and do something similar here. We're going to create ourselves a list, okay? And we're going to assume here that that those things exist, and we're also going to assume that get exists, okay? Add exists. All right, so we'll just assume and add like that. All right. Then what we're going to do here is write some tests for remove. So let's do a whole lot of adds. We'll just do these ones here. We don't need to put all these tests in here. Okay, because add is already being tested, right? We're assuming add already works at this point, and we can put this in if we want, just to make sure it actually did work. We just skip all those other tests, put this in. Okay, so we've added a bunch of stuff. Now we want to test what happens when we remove stuff. Okay, so l.remove, and we'll just say 1. Okay, so what should we get now? Oops, I didn't mean to say 10, I meant to say 1. What should we get now? Well, we should get, the size should be what? What should the size be, folks? If we remove something, the size should now be 2. Okay? And then we get rid of this. Yeah, and we get rid of this. Okay, so that's what we should see. And then we can remove 1 again. Right? And see something like this. Remove 1, and the size should be 1. And we're going to get rid of the C. Okay? And actually, given what we've just changed, we can actually test that it brings back the right thing. Okay, this is new. I'm making this up as we go along because string r equals l.remove. Then we should also test that r equals bbb, right? Assert true r dot equals bb. Oops. Typo. Like that. Okay? And then we can do the same here for the next one. R equals, remove that, and then we can test that R equals, what should it be? It should be triple C. Okay. Oops. Typo here and typo there. Did someone else type something else? Why are there spaces in the toString? Yeah, there's no strong reason, Benjamin. It's just we could do whatever we wanted to. Okay, we could put commas there or whatever, but for simplicity, we've just said there's spaces. It could be that. It could be that. It's up to Benjamin. The answer is it's totally up to us. We're going to write the toString method, so it's up to us. And I think for clarity, it's simpler to have a space between each set of elements. Otherwise, it's kind of harder to read. We could put commas. We could put all kinds of stuff. But just for simplicity, we've decided we're going to do it this way. But it's quite arbitrary. So your question is a good question. All right. So then we're going to remove element 0, and we'll cut and paste all this code here. And so we're going to remove element 0, and then it should return A, right? And the size should now be 0, and the toString should be equal to empty string. Okay, just like that. Then we can do the test of get, and we're going to do the same sort of stuff here. Let's cut and paste all that code there. Test of get. And the out of bounds thing we're going to do in the next lecture, right? And then we're going to say, we're going to cut and paste that stuff there to make sure this stuff worked. Test of get, there it is. Okay, so the size should be 3. And then we're going to get something out of here, okay? So we're going to get 0, we're going to get 8, 1, and so forth. So we'll say assert true, L dot get 0 dot equals, what should get 0 give us? It should give us the string A, right? And then we can write the same thing over for the other elements in the list, okay? Okay, so then we're nearly done with this. Oops, oh goodness, I didn't mean to do that. Okay. Okay, and then we do get 1, and we should get BB, and do 2, and we should get CCC. Okay? And BB. There it is. Okay, so now we've written a test for get. Okay, again, very simplistic. And it's quite possible that when we write these tests that there are cases, important cases we haven't covered. Okay, writing comprehensive tests for this is actually an important job. You know, at one point, I was working for another company. I was working for Intel, and we we're building an entire JVM, and we had, I think it was 120 engineers working on it. They were all in Russia, and they had an entire group in a city called Novosibirsk, and their job was that entire group of roughly a third of the entire pool of engineers working on building this new JVM. 1/3 of them were just doing testing. Okay, all they did was build tests. They had an entire, like 1/3 of the entire engineering team was simply doing tests. Testing is a huge job, and it's a really, really important one. And we're only doing it. We're only just scratching the surface here. Okay, very important you realize that. Okay, so now let's just cut and paste this again. The same stuff. Whack it down here, and then we're going to reverse it and make sure L.reverse. Oops. L.reverse, and then we should see the list in the reversed order, like that. Okay, and then what we should do is remove some elements and see what happens. Okay, so just say L.remove 0, and then oh, what's another test? Someone's already suggested 2 things up here for reverse. There's another really simple one for reversing that we should probably do here. Can anyone think of a good test for reversing? No? There's a really simple test for reversing which we should be doing. It's kind of obvious. And that is, if you reverse a thing twice, it should go back to where it was, right? So let's just do that. So we'll say L.reverse like that, and it should go back to this. Right, so if we reverse and then reverse again, we should go back to exactly where we were at the start. Okay, and then we'll remove the CCC, and the 2 strings should be this. There it is, and it should be like that. And then we reverse that. Whoa! I just lost Teams. If you're listening on the streams here, just know that my Teams just completely died. Sorry, folks. Okay, reverse empty. Yep, we can do reverse empty. My Teams is back again. The application just crashed. Okay, so we're going to remove element 2. We get this, and then we're going to reverse it. And we get this. When we reverse it, it should just be like this. And then when we get to the smallest, we'll end up doing this, exactly what someone suggested earlier on. Oh, did everyone lose Teams? Awesome. All right. I'm glad it wasn't just me. Okay. Okay, we do that, and then we'll do the same thing again. And we'll bring it down to 1 element, right? And this is the very simple base case that someone mentioned earlier. The base case is that we only have 1 element in there. So actually, let's just do this again. We'll reverse it again, right? You follow the same pattern. Make sure we can always reverse it back to how it was. Right, so we've done that. So, okay, everyone follows this. I'm sure one of the tests we're doing here is every time we contract it, we test whether it reverses correctly. Then we're flipping it back again and make sure it comes back to where it was. It should always go back to where it was, okay? It's a very simple test we can do that tells us something about reversing. So we're going to remove this now, and now the string should just be A, right? And obviously, when you reverse that, it should just be A as well, right? And there's not much point in reversing that again. Okay, and then finally, we can remove the last element and then remove 0. Oops, remove 0, and then we should get empty string, and we should be able to reverse empty string and still see empty string. Okay, so let's just do that. Okay, we've written ourselves a bunch of tests. Any errors there or issues there? Okay, if anyone has anything to say about that, let me know now. Otherwise, I'm going to move on, and we're going to actually start implementing the array list at last. Okay, array. This is what the first part of the lecture is really supposed to be about. I've been a bit slow. Okay, so the first question is, what do we need? Okay, so now we're implementing the array list. Everyone follow me? Let's just recap. We wrote ourselves an interface. There's the interface. We made 2 empty implementations, a linked list one and array list one. There's the array list one. Okay, we made these 2 empty implementations. Then we wrote tests, which test all the different things in there. They're very basic tests, but they do test all the major things in there. Okay, the question now is, let's go and implement this array list. First question is, what do we need to make this array list work? There's something very obvious we need in this array list. What is it? Anyone? No suggestions? Yeah, what was that? Can you just say again?
Constructor.
Yep, we need a constructor.
Sorry.
There's something concrete that we need for the list. What is it going to be? What? Oh yeah. So Brendan pointed out something very obvious. All right, thank you, Brendan. Yeah, what I didn't do in test-driven development is make sure they fail, right? Of course I should, right? Brendan says you should run the test. Of course I should, right? I'm getting very distracted by all the technology issues. I'm sorry about that. But let's just run those tests. And yes, they fail. Okay, that's exactly what we expect. And of course, I should have done that before I started. Okay, before I started building the array list, and Brendan saved us from making that embarrassing mistake. All right, constructor, the way to store data. Yeah, that's exactly what I was getting at, James. Lewis asks, how many tests we need to write? That is the ultimate question, Lewis. There's no simple answer to that, okay? How long should the string be? That's kind of like, I mean, literally, it's like how long's the proverbial piece of string? There's not a simple answer, Lewis. And part of that's experience, right? Getting a sense of how long the how many tests you write, okay? And in this case, you know, I'm just frankly limited by the amount of time we have in a lecture to write the tests, but you need something more than this. And you will have seen already in a number of cases in the assignments and the exams that it's really easy to miss a case in your tests. That is, to have tests that pass even though there's a bug that we notice in the actual code. So the tests have not identified the bug, right? So that's a really good question, Lewis, and it doesn't have a simple answer, okay? There are people who spend their entire research careers trying to answer that question. All right, so what I was getting at here, folks, was for an array list, we need an array. That's really what I was trying to get at, okay? So we want an array list, we want an array. My next question is, how big is the array? Anyone? How big is the array? How big should I make the array, folks? I've got to make an array here. No one's going to make a suggestion? So I'm going to start typing, and hopefully someone says 8. Good answer, James. 8. Well, my question, Harry, is 0. That's also not a bad answer either, right? 10. Someone says 10, right? We can have votes on this. So what's the correct answer? The correct answer is that this is actually a really hard question, right? This is actually an incredibly hard question. What's the advantage of making a bigger array? It means you don't have to grow it as often, right? But on the other hand, if you make a big array, that means you may over-allocate, okay? Because if we only have 4 elements in the array, what's the point in having 1,000, your thing starting off as 1,000? So normally what we'll do is we'll have a modest size and we'll have a growth factor. There's another element to the question, which almost goes back to Lewis's question about tests. Should our tests help guide us when we're building the code right here in class about how big to make the array? And I'm going to suggest, yes, it should. We should make it small. And we could do exactly what someone has suggested and make it size 0. Okay? But even if it's size 0 to start with, we want to allocate something. How big should it be when we allocate that thing? How big should be the first thing we allocate? Okay? He's over-allocating arrays, the reason why Chrome uses so much memory. Good question. It's some of it's to do with Chrome, but a lot of it has to do with the web and the way people use the web and the way people use JavaScript and the way people write apps that go in JavaScript. But that's a question for another day. It's a really good question though. So what we're going to do here is we're going to allocate the array. And what I'm going to say is we're going to start off with an array size of 2. The reason why we're going to have an array size of 2 is because our tests had 3 elements in them. So we want to allow our test to exercise the question of whether or not we can expand beyond the minimum size of 2. Now 2 is a pretty crazy small size. We probably want more like 20 or 10 or whatever, something bigger in practice. But for the sake of exercising our tests, let's say 2. And someone said that in the chat. Yeah. Okay, so let's do that. All right, so the first thing we're going to do is here we're going to have a private array of type T for the values. Now here's another bit of unpleasant Java stuff here. We can't actually allocate a new T of 2. No can do, right? Try and do that. Java won't let you. Okay, that's what we want to do, right? We want to do we want to do that, right? Essentially, but Java doesn't let you do that. Okay, so what do we do? It's ugly. Okay, you can do that in C#, but you can't do that in Java. So what you have to do is this: you have to say like this, and instead of saying T, we make an array of object. Okay. And that is because of a feature of Java in the way it does generics. what's happened here? Now I've gone and, oh, I'm missing parentheses. Yeah, okay, so that's, okay, all right. So then, actually, what instead of saying 2, let's do this nicely and say initial size like that, and then in here we'll say initial size. Okay, and we can change that later, right? So we'll change that to something like 10 later on because it's going to, the performance isn't going to be so great. The other thing we probably want to do is have a growth factor, which means that if we run out of space, let's grow it, but don't always grow it by 2 elements, say, or 1 element. That'd be really bad, right? If you added 1,000 elements, you have to resize the array every time you add an element. Instead, let's grow it by some factor, okay? And for no particular good reason, we're just going to say we're going to grow it by 50%, okay? So we'll say private static final float growth factor equals 1.5f, right? So it's 50%. Okay, so each time we run out of space, we'll make the new array be 50% bigger than the last one. Okay, and then all right. So now we've got the value. What other thing do you think we need? There's some other key data structure here. We've got an array of values. Okay, I said value. I should say values. Okay, that's an array of values. That's the key part of this data structure. There's one other key thing we need here. What is it? Anyone? Any suggestions? Size, yeah. Well, yeah, the number of elements, right? That's a key thing we need here. So we're going to say here elements, right? Int elements. That's how many we've currently got. And it's interesting. So it's actually an important distinction between the size and the elements. So size here should return, let's just type it in now, elements, like that. Okay, so size should return the number of elements, which is different to this size. Okay, because this could, in general, might be bigger. It may or may not be bigger, but it could be the same. Okay, so our array here might be of size 100, but we may have only put 2 things in here. And when someone says size, we need to return how many elements, not the size of this values array. Okay, so it's an important distinction between the size of the values array and the number of elements. So when someone says size, we need to return the number of actual elements in the array. All right. So it's not the capacity, just to be clear, Adam, it's not the capacity, but the actual number of elements in there. All right. So now let's go and test. We're going to do test add. So to test add, we need to do 2 things.
No, I was talking about the...
Oh, how big is the array? Yeah, good.
About the actual array size itself, the capacity.
Yep, that's exactly right. So Adam was saying that he's talking here about the size of this array. That is the capacity of our data structure, whereas this here is how much is in the data structure at any point. Okay, all right, so now let's keep moving. I'm a little bit anxious that we're running slow here. Let's start off by doing the toString method, I think. Yep, so we've already done one part. We've added the size in with. So when someone says what's the size, we return the number of elements. Now let's write our toString method. Override, and we're going to override public string toString. And how are we going to make the string? Well, the simple way to do that is to start off with a string which is empty, and we'll call it RTN, which is short for return. Okay, so we'll call it RTN, and then we'll add stuff onto it. Okay, so and the way we're going to do that is going to say for int I equals 0 to what? How far do we need to go? The size of the array? No, the size of the array, as Adam points out, is the capacity. That's not what we want to print out. We want to print out the number of actual elements, because the array can be bigger than the number of elements in there. Okay, and it generally will be. Okay, so we want to say I is less than elements. We say I plus plus, and then we'll just add each element into this list, and then we can say this. We can say RTN plus equals that string concatenation. Now, if I is 0, we need to have spaces between them. Okay, but one way to do that is put a space in front of everything except the first one. Okay, you follow me? So we'll say if I is equal to 0, then no space. If I is greater than 0, we'll add a space. space. Okay, there you go. If I0 were out of space, otherwise, greater than 0, the out of space, otherwise you have nothing. And then you concatenate that with the value. Okay, so values of I. That makes sense? Okay, so what we're doing is we're putting a space in front of the value if we're not the first one, because we don't want to have a space in front of all of them. You only want a space with everything except the first one. So that's what that little thing with the ternary operator does. Okay, and then finally we have to return that thing. Return RTN. Now, look, I'm going to write this out longhand as well. I know we're short on time, but I know people will get confused. So let's just write it out longhand as well. If I equals 0, then RTN plus equals space. Sorry, I is greater than 0. Then you add a space in front of the return, and then you say RTN plus equals values I. Okay, I've just written the same thing here. It's in 3 lines of code. There it's in 1 line of code. I find that easy to follow if you know the syntax. Now, if you don't know the syntax, that's horrible, right? But if you do know the syntax, I think that's a little bit easier to follow than this here, which looks kind of more complicated, I think. But anyway, that's a question of taste. But you can do it either way, and I've written it out both ways so that you can understand the both different ways of doing it. Okay. Now, now we're going to do the add. So how do we do an add? Well, the first thing we need to do is to make sure there's space, right? So how do we do that? Well, we know how many elements are already in the array, which starts off at 0. Remember, in Java, everything gets initialized to 0 unless you say something else, right? So the number of elements will be 0 because we didn't say otherwise. So if elements equals the length of our backing array of values dot length, then we're out of space. Okay. Now, what we could do here is make this will work. Notice this will work if we don't have anything here at all. We don't allocate any space here because 0, well, okay, we could say values is, yep, okay. If value is null or that, okay, well, let's, all right, I'm just accommodating the suggestion before. Someone said, why don't you just start off with nothing in the backing array? Well, if we do this, that will work, okay? But that's not what we're doing, so I'll get rid of that. But I just wanted to show you what it would look like if you did do that. All right. So now we don't have any space in the array. We're out of space, so we need to grow the array. So what do we do when we grow the array? Well, first of all, we need to allocate some extra, and then we need to copy everything out of the old one into the new array. Okay. And then switch the new array becomes the default. Okay. So you can't simply grow an array. That's the problem here. You can't simply grow an array. So we need to make a new array, copy the old stuff into the new array, and then make that new array the default. And so to do that, we need a temporary variable. So we're going to make an array of type T, and we're going to call it TMP, right? That's going to be the new array. And we're going to do the same stuff as we did here, but it's going to be a different size. What size is it going to be? What size is this going to be? Can anyone remember? Well, we're going to take the current size and we're going to grow it by the growth factor. Okay? So we can just say turn it into an int, and we'll say values.length times the growth factor, which will be 3 in the first instance, but it will be different each time, right? Each time we grow it will be a different number. But the first time we grow it, in this case, it'll be 3. What's going on here? Why is that unhappy? Cast to int. I thought I just did cast. Oh, I didn't put parentheses here. Okay, I need to put parentheses around the whole thing, and then we're good to go. Okay, so I had to turn that floating point number into an int, because when you create an array of objects, you've got to pass an int. So now we have a new array called temp. Then we have to go and copy all the old stuff into the new one. So we say for int I equals 0, 0 I is less than values.length, I plus plus, and then we'll just say tmp I equals values I. So we're just copying everything out of the old array into the new one. Now the new one, which is called temp, is the same as the old one except bigger. It's got the same content in it except bigger, and the other ones will just have null values in them. So then we update values to be equal to the thing we just allocated, like that. Okay, so now we have ourselves a grown array. So this is need to grow. Okay, that means we're out of space, need to grow. Okay, so then once we know that we've got enough space, we can do this. We just add in the element that we're given. Elements, that's the last element in the array, equals value, and then we can say elements plus plus. As a shortcut, we can actually do the following. I'm going to show you the shortcut as well. You can just do this. Right, I'll comment that line out. Just for clarity, I'm going to write longhand, but you could have just written it in one line like that. Okay? So what that does, the plus plus means take the value of elements, index values, and put value in there, then increment elements afterwards. That's what that does, which is exactly what we see here. So the two things are equivalent. I've just written out longhand. All right, so now we have written add. So with a bit of luck, our test will actually give us a pass on add. Let's just see. We do. Fantastic. So now we have add working. Excellent. So now let's do remove. Now remove is pretty simple because we don't have to grow anything for remove, right? It doesn't matter if the thing contracts. Okay, so all we need to do here is reduce the number of elements. What else do we need to do? Oh, we're going to return something here. So it's going to be type T, trtn equals what? We're going to return what? What are we going to return? Anyone know? We're going to return values index. Okay, that's what we're going to return. And at the bottom here, we're going to return RTN, like that. Okay, now, once we've grabbed it, we need to actually get rid of it. Okay, so we wanted to grab it before we got rid of it. Now we're going to get rid of it. We're going to contract the array down. So to get rid of it, what do we do? Can anyone suggest what we do? Well, all we need to do is slide the arrays across. So slide across all the values that are higher than index and move everything down by 1. Okay? That's all we need to do. So let's do that. We can just write a for loop for int I equals index. I is less than elements. I plus plus. Okay, and then we just say values of I equals values of I plus 1. All right, and that will contract it. Now let's see if, we haven't done get. We need to do get because the test for remove won't work until we've done get. Can you see how to do get? Get's really simple. All we need to do is basically this. We just return that, values of index. Now notice at this stage, we're not taking care of out of bounds issues and so forth. We're going to do that in J15 when we look to see if things are out of bounds and learn about exceptions. Let's just test to see if get and remove are working. They are. So now we have everything except, don't you need to use a tolerance in a control statement for typecasting a float to an int? So, well, yeah, actually it really doesn't matter how that rounding works as long as it doesn't keep rounding down to the same value. Okay, I don't really care if it's exactly how that rounding works very much, as long as it's growing by roughly that amount. Okay, so you could. So never contracts the size of the array. Julian asked, we don't contract the size of the array. Absolutely, you're absolutely right, Julian. And you would want to do that under certain circumstances, right? You would want to contract it, but in our little example, when we do the remove, we do not contract it. That's what Julian's pointed out here, is we don't make values smaller. We don't reallocate values to a smaller values array. Now the question is, when would you want to do that? Well, if values gets too big and it's got enough dead space in it, maybe then you want to contract it. You could use something like the growth factor to say, well, if we're only using half the array, then maybe we should contract it. Okay, good question. We don't do that here in our simple solution. Okay, now the last thing that's remaining is the reverse. Okay, so all we need to do now is reverse the thing, and the simple way to do that is just to flip all the values around the half point. Okay, so just exchange all the values pivoting on the halfway through the array, right? Halfway through, not the array, but the elements, okay? Not the array, the elements, okay? So we'll go like this. We'll say for int I equals 0, I is less than elements, not the array size, but elements divided by 2, I plus plus. Okay, so that's going to get the first half of the elements. Okay, notice there is rounding here as well, but the rounding is going to work in our favor here, because it will mean that if it's an odd number, we just won't do anything with the middle, which is exactly correct. Okay, so if you've got an odd number of elements, you want to change the ones either side of it and not the middle one. Whereas if you have an even one, you want to change the ones on both sides of the middle. Okay, so the fact that this doesn't this rounds down from the middle is actually what we want. All right, so then what we want to do is we need to create a temporary value. Okay, and then so we create a temporary value t, temporary value t, and we'll say that is equal to values of elements equals values use of I. Okay, so we're going to remember that one. Okay, that's the one in the lower half of the array. And then what we're going to do is going to overwrite that guy with, so we're going to say values of I is equal to, we're going to overwrite it with the one in the higher part of the array. So that will be what? It's going to be elements minus 1 minus I. Okay, so it's going to be values. So we're working our way down from the top end of the array, right? So it's going to be values of elements minus 1 minus I. Elements minus 1 is the highest element in the array, and minus I means it's working its way down. So we're flipping them like this, okay? Like that. And then we'll say this guy is equal to temp. So we've just flipped these two values, okay? Equals TMP. Okay, so we flip the two values, and with a bit of luck, that will work. Okay, so we now have finished that whole section. We've implemented, let's just do a recap, folks. It was a long chunk, but what we did is we talked about abstract data types. We talked about the fact that a list is an abstract data type, and linked lists and array lists are concrete instances, okay? And then we went and wrote ourselves a very simple list interface. We made empty implementations of the two things. We wrote ourselves a set of very simple tests, not complete. And then, for one thing, they don't handle exceptions, which we're going to do in J15. And then we went and implemented the array list from scratch. So we've gone to implement our first concrete abstract data type from scratch just here. In this class, we're going to go and do linked lists. We're going to do sets, and we're going to do 2 implementations of sets, and we're going to do 2 implementations of maps. All right, let's move on. We're a little bit behind. I went a little bit slower than I had intended, but that's all right. Okay, so now we're going to do a list interface and its implementation. Okay, so so remember there are 2 different ways of doing it: arrays, which we've just gone and done, and the linked list. Okay, now linked lists are a natural way of implementing a list, obviously, but they have the downside. We looked at this before. The downside is to get element C, you've got to walk all the way down to the 3rd element in this example here, and which is fine for a 3-element list, but it's not so great if you've got 1,000,000 elements in your list. And we often build things with millions of elements in them. That's not at all unreasonable in computing. Okay, so you actually do have to think about that. And there's an enormous difference between getting something in 1 axis and getting it in 1,000,000 accesses. Now, here's a really interesting question. How do you reverse a linked list? Okay, and there are a few different ways of doing it, and I'm just going to walk through one. One of the things I like to do when we're not doing things remotely is actually get you to do it. I normally call for volunteers, and get you to do it yourselves. One of the things I like to think about is a recursive list reversal algorithm. A recursive list reversal algorithm makes the observation that you can that reversing, as someone pointed out on the chat, reversing a list of size 1 is trivial, right? Because a list of size 1 is itself, okay? And then what you can say is that to reverse a recursive algorithm at some level is very, very simple and elegant. It just says, to reverse a list, all I need to do is to make everything upstream of me be downstream of me and reverse it. Okay, so the stuff upstream of me, I'll treat that as a list and I'll get it to reverse itself, and then I'll just put myself behind it in the list. Okay, so what that means is in this picture, in this picture here, I'll say, okay, if I'm here, I'll say, hey, reverse all this stuff, right, which would then turn out to be a list D, C, B, and put me behind B. So that would mean it would be B, C, D, A. Okay, so that, sorry, D, C, B, A. Okay, so that makes the observation that the base case of list reversal is trivial. Reverse myself is straightforward. And to reverse an entire list, all I need to do is look at the first node in the list and reverse everything downstream of it and move that first node to the end of that list. Okay, that's the basic algorithm. Now let's look at this. One way is to do list reversal. There are two basic algorithms. One is to create a completely new list, okay, and the other one is to do the pointer reversal. So creating a new list, we can say the new start is over there. Now notice here we've got this start reference, this end reference, and each one of these things here is a linked list node. Okay, they're linked list nodes, and you've got the special reference here which points to a linked list node, and this special reference here which points to a linked list node. And let me just show you again this here. This is what you see here. You've got a linked list instance here which has 4 elements in it. It's got a reference to the first, a reference to the last. It's in the middle of doing something, so they're both pointing to the same place in this example, which they shouldn't, but just in this moment in time when I've shown you they are. So the first goes to here, it goes to there, it goes there, but the last should be pointing over here. Maybe if I step forward, oh well, it's not quite. Sorry. Oh well, I can't show it to you right now, but they're the data structures you need. Okay, so these ones here are each the same, and they have a value, which is A here, and a reference, which here points to that one there. Okay, so one way to do it is to create a new list with a new start and a new end, and pluck all the things off here and putting them at the end sequentially. Okay, and so you just move them one at a time. Each one goes to the start of the list. So you start off with A, that's your new list and your new start, and then you take B and make it the new start, make it refer to A, then you take off C, make it, and so forth, and just go like that. All right. And another way is you flip all the pointers. Okay. Which is a kind of elegant way to think of it. If you can work out how to flip all the pointers, because they just go in the other direction. It's a pointer reversal trick. What we're going to do in our so I'm going to show you the next mini quiz. What we're going to do is we're going to use a recursive method, which is the one I basically described a moment ago. So let me just make this poll visible, and we'll jump to code. We'll code these examples up right now. So I'm going to copy this. Copy and paste it, the whole thing. Cannot copy because I didn't have the right name. Paste. Okay, I can't do it like that. I need to create a new folder. New package, A02. There it is. And now what we're going to do is copy all these things here out and paste them there. Hang on. Copy them there. Okay, so now what we have is, and we'll get rid of all these other ones. It's going to confuse the heck out of me if we have 2 versions of everything. And there we are. Okay, so now we'll get rid of that. That was the last module. Now we're here. Oops, there it is. So that's our interface, and I just duplicated everything over, okay? Hopefully everyone can follow me. And we've got the array list there, okay? We just did all that. Now we're going to build a linked list, and we've got our test. Now let's change this here to false. So we're testing the now the linked list, as Brendan pointed out earlier. We want to make sure we test it and it fails first. Okay, great. So it's failing, and so what we have now is an empty linked list implementation which fails. And let's go ahead and try and build up our linked list implementation from there. All right, where are we? Yeah, okay. So the first thing I'm going to suggest we do is make an inner class here, which is like a linked list node. We'll call it LLN, which is a linked list node, okay? So we'll say class LLN, linked list node, will be one of those little nodes in the linked list. So what should be in the linked list node? Can anyone suggest what the linked list node should contain? a node and a linked list. I'll give you a clue. It has two things. Yeah, a value and a pointer. Great, exactly. Okay. The next thing in the list, which is the reference and the value. Right. Okay. So and the type of the value is going to be type T, value, and then it's going to have a reference to the next one, and the type of it is going to be LLN, linked list node. Okay, and that will be next. Okay, so it's going to have those two things in it: a value, which is the list element, and a next. Okay, and then we need a constructor to make one of these new things. Okay, so we'll say public LLN, linked list node, T value, that's the value, and LL next, that's the next one on the list. LLN, sorry, next, linked list node next. So when we create a new one, we say that's where you're going to point to next. Okay, so we say here's a new node, and that's what it's going to point to next, like that. And then we'll say this, very simply say this dot value equals value. So this is very, very simple. Nothing very deep or interesting here yet. It gets more interesting in a minute. Okay, just like that. Now, the other thing we want to do is have a toString which captures the entire linked list from this node onwards. So we'll say, and what we can do is we can say public string toString like this, and then all we need to do is if our next has nothing, that is, we're at the end of the list and we don't need a space at the end. Otherwise, we'll print the value followed by a space. Okay, so we can say if next equals null, which means we're at the end of the list, we don't need a space. Okay, then we'll return value.toString like that. So we just return that. Otherwise, we return, we actually notice the reason why I wrote toString. Some of you wonder, why did I even do that? Well, if you don't do that, you get this. There's multiple ways, because it doesn't know, Java doesn't actually know how to turn that value into a string. There's some strange ways to deal with this. One way to do it is say, return an empty string followed by the value. The other way to do it is to do it explicit and say value.toString. We can just do it this way, or we can do it the other way. Okay? But that's what's going on there. That's why I have to say return value.string. So otherwise we can say return value followed by space followed by next. Okay, I'm going to rewrite all that code to make it easy to follow. I think string rtn equals value. Right, that's us, and we can put a empty string there to force it to be a string. Okay, so what that means is we're going to by default just return the value that's at this node. And then what we're going to do is we're going to say if next is equal to null, we're done. If it's not equal to null, then return gets rtn. We add on to, okay, so what this says is if there's something after us, then what we need to do is to add all of the stuff after us, okay, with a space before it. So we say return is equal to whatever we had, that's our value, plus a space, plus next. Okay, and next is of our own type. So what that's going to do is it's going to call toString. And then, so we've got a recursive implementation of toString. Okay, a recursive implementation of toString. And then finally we return rtn. Okay. And again, I could write that in the shortcut way. Let's just do that. The way I would do it is this way. Return, you would say return you can write it all in one line like this. Okay, return value plus the following. Oops. Like this, followed by a space, followed by next, otherwise empty string like that. Okay, so that's the alternate shortcut way of doing the whole thing. I'll just put that at the top because that's a one-line answer to the entire thing. Oh, damn, sorry. Keyboard issues still. Apologies for that. Put it up there. Okay, so that's a one-line way of writing it, and this is the multi-line way of writing it, which may be clearer. All right, so we return our value, and if we have something following us, then we return everything that follows us. Okay, and now we have our node. Okay, so then the next question is, what do we do if we need to add? Remember, our first test we have is for adding something. If it was doubly linked, okay, so the good question. James asks about doubly linked list. This is a singly linked list. Okay, this is a singly linked list. And if it's doubly linked, things are more complicated. Doubly linked lists are really useful, but singly linked lists are simpler. The advantage of a doubly linked list is that you can go backwards and forwards. With a singly linked list, you can only go forwards. But when you have a doubly linked list, then all these operations become a little bit more complicated. Okay, I won't go into it now, James, but I'll just suffice to say that at the moment we're just doing singly linked lists. Okay, now let's do an add. So what's the what do we have in this linked list class? So we're finished. I believe we're finished implementing our LLN class. So now let's get on with implementing this whole linked list. Okay, and what I suggest we do here is we need to refer to the start and the end of our little chain of linked list nodes. So I suggest we have LLN start and LLN end, like that. Okay, actually, what we normally do is we say first and last, and last. Okay, so that's going to refer to the first and last nodes in our list. Okay. What else do we want in this data structure? Something really basic and fundamental. Anyone? We want, just like the array list, we want to count how many elements there are. So we're going to say int elements, like that. Okay? So we've got a first pointer in our linked list, a last pointer in our linked list, and all of the elements in the linked list. Okay? So now size, down here, we can already implement this. Return elements. ToString, by the way, we can add that down here. Override string to string, and it will just return first, just that, return first, like that. Okay, so string to string. What's going on here? Oh, public. I've got to say public. I forgot to say public. Okay, you can't make the overridden method weaker or less visible than the one it's overriding. And because the one it's overriding is public, I've got to make this public, and that's what it was complaining about. I didn't have public there. Okay. So now the ToString method for this class is very simple. It just goes to the first element in the list and says, now turn it into a string, right? And we already wrote that code here. Okay. So it'll just go to first and it'll implement this. It'll do this code here. Okay. And elements is simple. We just return the number of elements. And so now when we do add, first thing we need to do is find out, do we have nothing in our linked list? That's a special case, okay? Otherwise, so there's two cases basically. There's either nothing there at all, right? This is the first element being added. Otherwise, all the other cases are the same. So the first thing we'll do is say if, oops, caps lock, if next is equal to null, not next, I mean first. If first is equal to null, that means we've got nothing in there, okay? So, actually what we can do, like this, LLN is, all right, so the first thing we do, regardless of whether there's something in the list or not, is we have to create a new node, okay? And it's going to take, that new node will have two values in it, or two things in it. One will be the value that it's holding. The other one is what? The pointer to the next, okay? Now, if we add this at the end, then we can make that thing, the next value be null, okay? So we say null, like this, okay? If we keep adding things to the end, then the thing we just added, its next will be null, okay? So it's always going to be the case that the last element on the list points to null, okay? And whenever we add something, it will go on the end of the list. Therefore, its next will be null. Okay, so we've gone and made ourselves a new node, a new linked list node there called LLN. Now, if first is equal to null, then we need to say first equals LLN, and last is equal to LLN. And you know, we can actually write it like this. So you can write both assignments in one statement, just like that. So now you've said, okay, there's nothing here. All I need to do is make first and last both point to the thing I just allocated, then just created, just like that. Otherwise, we have to do something a little bit more interesting. Whoops. And that is, what do we need to do? Okay. Well, we need to. We're not going to change first. If there's already a first, okay, then we're not going to change first because we're putting this thing at the end. All right. So what we do need to do is we need to make last refer to this thing we just allocated. But before we do that, we need to make the thing that's currently last refer to the thing we just allocated. Okay. So we're adding it into the end of the list. So we need to go to the end of the list, make the last thing in the list refer to the thing we just allocated. Okay. And then the thing we just allocated becomes the end. Okay. So we'll say last equals LLN. But before we do that, we need to, before we do that, we'll say last dot next equals LLN. Okay, I think that's right. So what that's saying is go to the end of the list, which we've already got a reference to. That's up here. Okay, so find the node at the end of the list, make it refer now to LLN. Previously, the one at the end of the list referred to null. Okay, so now it's going to refer to LLN, and then we're going to make last refer to LLN. And we can, just like before, we can do this yeah. So we just do it like that. And that should do it. We now should have add working. We've done size, we've done toString, we've done add. So let's just run that. And hopefully we get add passing. It didn't. Okay, so what have we done wrong? Assertion. Okay, so we're going to debug this, folks. What have I done wrong? This failed here. It failed. Oh, the size was wrong. Aha! What have I done wrong? Folks, can anyone see what I did wrong? Look here. The failing test says assert true, size is equal to 1. Okay? But if you look here, we didn't actually add anything to the size, the number of elements. So we need to increment the number of elements, and we do that here. Okay? So now let's run that again. Okay, and we've got add working. All right, so now let's do remove. Okay, let's do get. We should do get first because that's a simpler one. Okay, now one way to do this, which is going to help us in the future, is to write ourselves a private method called get LL, which will get the nth LL on the list. Okay, so we're going to do that first. Which will get the node. So get actually gets the value, but let's write a method which actually gets the node, the last node in the list. Okay, so we'll say private LLN get last, like that, and then or actually get the one at a particular index. Get LLN, okay, int index, okay, and then all we need to do is how do we get the linked list node at a particular index? We could write a for loop for that, right? But another way to do it, which is kind of the recursive way to do it, is to say if index, actually we need to provide the starting point too. Say LLN start, so it'll be the offset from this position. We'll say if index equals 0, then we return ourselves. We return the start. Okay, so someone says get us the go 0 steps into the list, well, that means return the start. Otherwise, all we need to do is say to the rest of the list, give me the index minus 1th element for you. Okay? So if I've got a list here and it says, give me the index element, that's like saying, give me the index minus 1 element of the remainder of the list. Okay? So else return get LLN of start.next, comma, index minus 1. All right, so now we've written a recursive method which will get the index element of the list. So now we can write our get method and we can say return get LLN of first, comma, index, and then we'll take the value of it. Okay, which is because we need to return the value for get. Okay, so now we've got get implemented. Hopefully, let's see if that worked. There you go. Gets passing now, and now let's implement remove. Okay, and then we're just about done, and we're just about out of time too. But let's finish this off. So we're gonna. Okay, so the first thing we might want to do is get the prior node. Okay, so first of all, if the index is 0, that's a special case. Okay, so if we're going to remove the first element, then that's special, because if it's not the first element, then we need to know the one before it so we can fix up the next point to go around it. Okay, so if it is the first one, that's a special case. So we'll say if the index equals to 0, then this is actually pretty simple, right? Because all we need to do is say first of all, we'll have our return type here. We'll say t rtn, like that, and we'll say rtn equals first dot value. That's what we're going to return, because remember, we've got to return the value. So it's first dot value. Okay, so if it's index 0, it's the first one, right? Although notice here we haven't done a check to make sure that the question is a good one, and that's because we haven't implemented exceptions yet. So in J15, we're going to have to put a thing here to say, hey, if you're asking to grab an element which doesn't even exist, then we need to throw an exception. We're not going to do that in this lecture. We're going to do it in the next lecture. So we take the first value. That's what RTN is. Okay, and then what we're going to do is going to say first is if the first is equal to null. Actually, yeah, so what we're going to do is going to say first is equal to first dot next. Okay, so we're removing the first element in the list, so whatever comes after first is now going to be the new first thing. Now, if that was the only element in the list, then its next would be null, which means we need to fix up last as well. Okay. So we need to make sure we're not removing the only element in the list. So if first equals null, then last equals null. Okay. All right. And then finally, right down the bottom here, before we return our value, we've got to say elements minus minus, and return RTN. Oops, return RTN. Like that. Elements minus minus. Now we've got this if statement, the other half of the if statement. So if it's not the first element in the list, then what we want to do is to get the element prior to the one we're removing. Okay, it's not the first one, so we need find the one before it. Okay, then we can fix its next pointer to the pointer the one after it. Okay, so now what we'll do is we'll say LLN prior equals what is it? Get LLN start comma index minus 1. Right? First, sorry, not start, first. Okay, so what that's going to do is it's going to find us the element before the one we're going to remove. Okay, now what we're going to do is going to say prior.next. Oh, hang on, we've got to get our return value. So RTN equals prior.next.value. Okay, so the thing we're going to return is the value of the thing after the prior. Okay, a little bit twisty, but that's what we're going to do. So now we've set RTN, so we're good to go. We can now remove, now we've found RTN, we can remove the node from the list. So now we say prior.next is equal to prior.next.next. Okay, so we're skipping over it. Okay, so we're saying the one before the one we're going to remove is going to refer to the one we're going to remove, whatever came after it. Okay, I can make this slightly simpler for you. LLN target equals prior dot next, like that, and then we can just say return equals target dot value, and then we can say prior dot next is equal to target dot next, like that. Okay, and now we've removed it. Okay, now the question is, now we've got the same question here, that if the if we now are referring to the end of the, if we've just removed the last element of the list, we need to fix up last. Okay, so if prior equals null, that means we just remove the last element on the list. We need to fix up last, so last equals null. All right, let's test that. Didn't work. Okay, so let's check out why. Okay. Oh, hang on, reverse. That's not what I want. I want remove. Let's run remove. Okay, there. Okay, remove. The very last one. Okay, so it didn't work here. It got down to, that's interesting. So our toString method didn't work once it got down to this. That's interesting. Okay, so look at what's happened here. We've done our remove. It's worked for here, for here, for here, for here. And when we remove this, we did get size of 0, but we didn't get an empty. We didn't get empty string. So I wonder what we got. That's very interesting. Maybe we wrote the thing in the wrong way and we gave ourselves a space or something. Let's just see that. Let's see what happens here. So string is going to be empty string plus whatever was the first. Now, if first, but what if first is null? If first is null, then return like that. And let's see if that fixes it. Okay, we didn't take the, we didn't get it. Yeah, I think we got null, but we didn't get a null pointer exception, which is interesting. Yeah, that fixed it. Okay, now what I'd love to do is to do the reversal, but recursive reversal is a bit mind twisty, and I know we've only got 2 minutes to go, so I think I'll leave that till the next lecture. So we're gonna have to leave that over until Friday. But let's look at what we did. Let's just back right up. We've started delving into abstract data types. We've looked at lists. We've looked at 2 different ways of implementing lists. We've written ourselves a little interface, which is like the Java interface except simpler, which has these elements in it. We've implemented 2 empty versions, an array list and a linked list with no functions in them. We wrote ourselves a whole lot of tests, very simple tests. We then went and implemented all of the array list, and we've implemented just about all of the linked list, and we've just run out of time. Slightly bummed. I was hoping I would get that all done in this lecture, but we expect to find the answers to them ourselves. No, sorry. Someone's asking about the class polls. I will try and give you answers to all the class polls. Okay, I haven't got around to it. I was hoping I'd do it during the teaching break, but the teaching break was a break from teaching, but it wasn't a break from all the other stuff in the world, unfortunately. So I haven't got around to it yet, but I will do that. Okay. So with that, let's just go to our last slide, which will be the bio. Actually, this is J15. Let's go to the bio. So the last slide is Barbara Liskov. Now, many of you will have heard me say lots of times that objects encapsulate state and behavior. Okay, Barbara Liskov had a lot to do with the early days and the early foundations behind object-oriented languages. Barbara Liskov is still, I think she's emeritus professor. If you come to my office, I mean, I haven't been in my office since March, since COVID started, but right next to my office is an enormous photograph of her, because we've got a whole lot of portraits, and she's one of them. Interestingly enough, her portrait was on the window right next to Tony Hosking's office. And Tony, who's a longtime friend of mine, she's his academic grandmother, meaning that she was the advisor of Elliot Moss, who comes and visits us often, and Elliot was Tony's advisor. But Barbara was the first. No, she was the second woman to win the Turing Award after Fran Allen, who we remembered recently. And she had an enormous influence on distributed computing, high-level programming languages, and particularly object-oriented languages. And as I say, her influence actually came directly onto me through me working for many years with Elliot, who was her student. And with that, I think we can finish the lecture. So thanks for joining us, and I hope the rest of your week goes well.